Here is something that will change how you think about AI. When you type ChatGPT into ChatGPT, the model does not see 7 letters. It sees 3 chunks: chat, G, PT, and the word indivisible. That becomes ind, IV, is, IBIL. 4 separate pieces. These chunks are called tokens, and they are the reason your prompts sometimes fail, your API bills spike, and your AI can write poetry but struggles with basic math. Every single thing a large language model does, reading your input, thinking about it, writing a response, happens one token at a time. Master tokens. And you master the language models themselves. Think of tokens as the atoms of language models. Just like you cannot understand chemistry without understanding atoms, you cannot truly understand LLMs without understanding tokens. A token is simply a chunk of text. Sometimes a whole word, sometimes part of a word, sometimes just a single character. When you send a prompt to GPT-4 or Claude or Llama, your text gets chopped into these tokens before the model even begins processing. The model never sees raw text, only a sequence of token numbers. You might wonder, why bother with tokens? Why not just feed the model one character at a time? Here is the problem. Language has structure. The letters THE almost always appear together as the. Processing them separately wastes computational power on patterns the model already knows. But using whole words has issues too. What happens with running versus run? Or words the model has never seen. Tokens hit the sweet spot between characters and words. The most popular tokenization method is called Byte Pair Encoding, or BPE. Here is how it works. You start with a massive text corpus. Think all of Wikipedia, millions of books, the entire internet. Initially, every character is its own token. Then the algorithm finds the most common pair of adjacent tokens and merges them into a new token. It repeats this thousands of times. So, T and H merge into th. Then the and E merge into the. Eventually, the and space merge into the I. This builds up a vocabulary of common patterns automatically. Once training finishes, you have a fixed vocabulary. A dictionary mapping every token to a unique number. GPT-4 uses roughly 100,000 tokens. Claude uses about 102. These numbers are called token IDs. When you type "Hello World," the tokenizer converts it to something like PyST 496 995. The model only ever works with these numbers. It has no concept of letters or spelling, just statistical relationships between token IDs. Let me show you something fascinating. Open the OpenAI Tokenizer tool. It is free and available online. Type artificial intelligence and watch it split into art, artificial, intelligence, 3 tokens. Now type AI, just 1 token. This is why abbreviations are so efficient. Type your name. If it is uncommon, watch it shatter into many small pieces. Type indubitably, 5 tokens. Type the, 1 token. Common patterns get single tokens. Rare patterns get fragmented. Here is where things get interesting for programmers. Code tokenizes very differently from English prose. A variable named getUserAccountBalance might become 5 or 6 tokens. Get user account bal ans. But X is just 1 token. This is why AI code assistants sometimes give bizarre variable names. Shorter names use fewer tokens, giving the model more room to think. Python keywords like def and return are usually single tokens because they appeared so often in training data. This explains why LLMs are notoriously bad at math. The number 127 might tokenize as a single token, but 128 might become 12 and 8. The model sees completely different symbols for numbers that are just 1 apart. It cannot count characters in a word because it never sees characters, only tokens. Ask it how many R's are in strawberry, and it struggles because strawberry is just 2 tokens to the model. It has no letter level awareness. You have heard of context windows. GPT-4 Turbo has 128k tokens. Claude has 200k. But what does this actually mean? The context window is the model's total working memory. Your prompt, the conversation history, and the response all share this space. If you use 100k tokens in your prompt, the model only has 28k left for its response. This is why pasting entire code bases sometimes cuts off the answer. You have eaten into the response budget. Context windows are not just input limits. They are total processing limits. Here is the deep connection. Transformer models use something called attention. Each token looks at every other token to understand context. With 1000 tokens, that is 1 million attention calculations. With 10,000 tokens, that jumps to 100 million. This quadratic scaling is why longer context windows cost exponentially more to run. It is also why responses with heavy context feel slower. Every token you add does not just add linear cost. It multiplies across every other token. Now let us talk money. OpenAI charges per token, both input and output. At current prices, GPT-4 costs about $30 per million input tokens and $60 per million output tokens. That sounds cheap until you scale. A customer service bot handling 10,000 conversations daily with 2,000 tokens each burns 20 million tokens. Roughly $600 in input alone. Understanding tokenization helps you write efficient prompts. Saying, summarize, instead of, please provide a comprehensive summary of the following. Saves tokens on every single call. There are hidden tokens you never type but always use. The start of sequence token tells the model a new conversation began. The end of sequence token signals completion. The padding token fills empty space when batching prompts together. System tokens separate your prompt from the model's response. When you see truncated outputs, sometimes a rogue end token triggered early. These control tokens are the punctuation of the LLM world. Invisible but essential. English gets the VIP treatment in most tokenizers. Hello is one token, but Namaste in Devanagari script might become 6 or 7 tokens. Chinese characters each become individual tokens despite representing whole words. This multilingual tokenization gap means non-English prompts cost more, use context faster, and sometimes perform worse. Newer models are improving this, but the bias remains. If you are building products for Indian users, factor in that Hindi prompts consume roughly 3 times more tokens than English equivalents. Let me give you actionable tips. First, front load important information. If context gets truncated, you want key details processed early. Second, use common words over fancy synonyms. Use is 1 token, utilize is 2. Third, test your prompts in a tokenizer before deploying. Fourth, structure with clear markers like dos and vertiod that tokenize predictably. Fifth, for code, use descriptive but short variable names. Finally, consider that output tokens cost double input tokens on most APIs. Optimize for concise responses. The field is evolving. Google's Gemini uses a different tokenization strategy optimized for multimodal input. Images become tokens too. Research into byte-level models could eliminate tokenization entirely, letting models see raw characters while remaining efficient. Tokenization-free architectures are being explored at major labs. But for now, tokens remain the fundamental currency of language AI. Understanding them separates casual users from power users. You now have that understanding. Let us recap what you now understand. First, tokens are chunks of text, not characters, not words, but statistical patterns learned from massive data. Second, tokenization affects everything from API costs to why LLMs struggle with counting letters. Third, context windows measure total tokens, including input, history, and output combined. This knowledge makes you a sharper prompt engineer and a more informed AI builder. Next up, watch our video on embeddings. How LLMs turn tokens into mathematical meaning. If this clicked for you, subscribe and leave a comment. What token behavior surprised you most? See you in the next one.